Greetings, class. Have you ever looked at a massive cargo ship? I mean, we're talking about thousands of tons of solid steel here, and wondered, how in the world does something that incredibly heavy manage to float so effortlessly on the water? It kind of seems to defy logic, doesn't it? I mean, you toss a tiny little pebble into a lake and it sinks straight to the bottom in seconds. Yet a colossal vessel just glides perfectly across the ocean. Well, today we will study principles of fluid mechanics, density, pressure, and upthrust. Okay, let's just dive right into this with our absolute foundational concept, density. Now, it is, quite simply, the mass per unit volume of a substance. Mathematically, we represent it by the Greek letter rho, which equals mass divided by volume. The SI unit you'll use is kilograms per cubic meter. Basically, density is just telling us how tightly packed the matter inside an object actually is.
Listed are the main insights for the heading discussed. Note them specifically since they are highly relevant for exams.
Now, what's really fascinating here is the stark contrast when you actually look at the numbers. Consider this data for a second. Air is incredibly light, right? It has a density of just 1.2. Water sits at 1,000. But step down to gold? No way, 19,300. A high-density material like gold is packing a massive amount of mass into a very tiny volume, whereas a low-density material like air contains drastically less mass in that exact same amount of space. So, let's see how that builds into our next fundamental concept, pressure. The absolute crucial takeaway here is that pressure isn't just about how hard you push. It is the force acting per unit area. The formula is beautifully simple. Pressure equals force divided by area. We measure this in pascals, where 1 pascal is just 1 newton per square meter. The golden rule you must remember: for the exact same amount of force, a smaller area creates a much larger pressure, and a larger area creates a significantly smaller pressure. And honestly, everyday life brilliantly illustrates this concept. Ladies, or really anyone who's had the misfortune of getting their foot stepped on at a crowded party, you already understand this physics principle intimately. Getting stepped on by a stiletto heel hurts infinitely more than a flat shoe, precisely because all that weight is concentrated into a tiny little point, exerting massive pressure. It's the exact same reason a sharp knife slices cleanly right through vegetables. You're concentrating the force on a microscopic edge.
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
All right, class, I need your absolute focus right now. We are beginning our first major mathematical derivation of this explainer. Liquids exert pressure simply because they have weight. It's that simple. Imagine a small point submerged at a depth h in a liquid. The pressure at that point is caused entirely by the heavy column of liquid sitting directly above it. Now, if we say the base area is A and the fluid density is rho, the volume of that liquid column is area times height. Therefore, its mass is density times area times height. Following that exact logic, we already know weight equals mass times gravity, right? So if we substitute the mass we just found, the weight of the column becomes rho times A times H times G. Since pressure is force over area, we divide that entire heavy weight by the area. And just watch what happens mathematically here. It's so elegant. The area completely cancels itself out, leaving us with our final triumphant equation: pressure equals rho times G times H. Make no mistake, this is arguably the most vital formula in all of fluid mechanics. So, consolidating that derivation, let's isolate the variables that actually survived. Liquid pressure depends solely on 3 things. First, the density of the liquid. I mean, swimming in a pool of mercury will crush you much faster than water. Second, the depth. The deeper you dive, the higher the pressure climbs. And third, gravity. Notice what is entirely missing from this list: the shape and the surface area of the container. They literally do not matter at all. Now, how exactly do we calculate the pressure difference between 2 varying depths? Trust me, this is a highly critical skill for your exams. If point 1 is at depth h1 and point 2 is deeper at h2, the pressure difference, delta P, is simply the pressure at point 2 minus point 1. By factoring out our constants, density, and gravity, we get our key equation, delta P equals rho times G times delta H. Put simply, the change in pressure is directly proportional to the change in depth. But wait, we absolutely have to clear up a massive misconception right now. Fluids are not just pushing down on you. A fluid at rest is in complete equilibrium, which means the pressure acts equally in all directions. It is crushing in from every conceivable angle. This is exactly why water violently pushes sideways against a dam wall and why scuba divers feel a uniform squeeze all over their bodies. If pressure only acted downward, well, fluid dynamics as we know it simply wouldn't exist. And let's bridge this theory right back to reality. You literally cannot forget the heavy, invisible blanket of our atmosphere. The air above us is actively pushing down on the surface of the water all the time. So to find the true absolute pressure at a certain depth, you must add the atmospheric pressure to the liquid pressure. For example, at a 10-meter depth in water, the liquid pressure itself is roughly equal to atmospheric pressure. Adding them both together gives you the actual absolute pressure crushing down on you at that depth. Which brings us perfectly back to our opening mystery. Have you ever noticed that a remarkably heavy stone feels incredibly light when you try to lift it underwater? This magical assistance you're feeling is a phenomenon known as upthrust or buoyancy. By definition, upthrust is the upward force exerted by a fluid on any fully or partially immersed object. It's the exact same reason fish swim gracefully and colossal cargo ships stay perfectly afloat. But why exactly does it happen? Let's connect the dots from our previous lessons. We just established as a fundamental law that pressure increases with depth. Therefore, if you submerge an object, the water pressure pushing up against the bottom of that object has to be strictly greater than the water pressure pushing down on the top of it. Because the bottom depth, H2, is deeper than the top depth, H1, the upward force violently overpowers the downward force. That difference? That's upthrust. So let's prove it mathematically. This is our second major derivation of the explainer, so stay with me. Upthrust, denoted as FB, is simply the upward force minus the downward force. Since force equals pressure times area, the difference in force is the difference in pressure times the area. We substitute in our previous rule, delta P equals rho G delta H. Now look closely at the final equation. Area multiplied by the change in height. What is that? It's volume. So we neatly arrive at the equation, upthrust equals rho times G times volume. Now I want to share a really vital memory trick with you. Do you notice the variables rho multiplied by volume? Well, density times volume is literally just mass hiding in plain sight. So rho times V is just the mass of the fluid displaced. Multiply that by G and you get weight. The magnificent conclusion here, the upthrust force is exactly equal to the weight of the fluid that was displaced. And this brilliant deduction perfectly illustrates the legendary discovery by the ancient Greek scientist Archimedes. Now, I require you to commit this exact phrasing to memory for your examinations. The upthrust acting on a body immersed in a fluid is equal to the weight of the fluid displaced by that body. It is an absolute universal rule. It applies to liquids, it applies to gases, and it applies to objects of absolutely any shape. So, the crucial point in this constant battle between gravity and buoyancy all boils down to a simple comparison. If an object is perfectly floating, it means the upthrust exactly equals the object's weight. It is in perfect equilibrium. If it's sinking, the weight of the object dominates the upthrust. And if it's actively rising to the surface, the upthrust from the displaced fluid is actively overpowering the object's weight. It's essentially just a tug of war. Let's pull all this heavy academic theory back into the real world. Why does that massive steel cargo ship from the beginning actually float? Because its wide hull displaces a massive volume of water, creating an upthrust that perfectly equals its heavy steel weight. It's the exact same reason submarines use ballast tanks to change their weight at will, and why strapping on a life jacket increases your body volume, displacing more fluid and guaranteeing enough upthrust to literally save your life. All right, class, let's hit our high-yield summary. These are the non-negotiable core concepts you must take away today. Density is mass per unit volume. Pressure is force per unit area. Liquid pressure is heavily dependent on density, gravity, and depth, which gives us P equals rho G H. Remember that pressure inside a fluid acts in all directions equally. And to find absolute pressure, you always have to add the atmospheric weight crushing down from above. And wrapping up with buoyancy. Upthrust only exists because fluid pressure increases with depth, meaning the bottom is pushed up harder than the top is pushed down. Archimedes' principle cements the rule that the upward buoyant force precisely equals the weight of the displaced fluid. Floating and sinking are simply a delicate balance between an object's weight and the fluid's upthrust. These are the rules that govern all fluid engineering. To wrap up this explainer today, I want to leave you with a bit of a puzzle to test your true mastery of these principles. Imagine you are suspended precisely in the middle of a fluid, completely still, neither floating to the top nor sinking to the bottom. What exactly must be true about your density compared to the fluid around you? Think carefully about the equilibrium of upthrust and weight. Until next time, keep questioning the world around you.
The screen presents essential keywords for this topic categorized by different exam boards. These terms need careful focus while studying as they are very important and should not be ignored at any cost. Moreover, past paper analysis for each board and paper type is also included. Pay close attention to this section as it will significantly strengthen your preparations. Also, make an effort to understand how each keyword is used in the context instead of just memorizing them separately. Regular use of these terms in past paper practice will improve your accuracy and exam performance.
Please subscribe our channel to get more educational videos. Thank you.